Next up is Ryder Fox from the University of Miami. Ryder's field is meteorology and physical oceanography. His advisor is David Nolan, and he's done practicums at Brookhaven and Pacific Northwest National Laboratories. All yours.
So as I begin, I'd just like to thank my co-authors who have supported me throughout the years of my research so far. Again, those are Brian McNulty, Honorelli Morales, my advisor Dave Nolan, and then Adam Barble. As the title here suggests, I'm looking at a spectrum of storms from hurricanes to mid-latitude continental thunderstorms, and I'm asking the question of how sub-kilometer grid spacing varying will change those storms if it does, and whether there's an impact to microphysical parameterizations. So as a background, my primary motivation has been to improve flooding forecasts. Currently, flooding is still a leading cause of death due to severe weather events. So we would love to be able to get as accurate of a model and warnings as possible, of course. And unfortunately, we still don't understand quite enough about how ice particles are formed in the atmosphere and how that lends to the precipitation that we're going to have that then accumulates and becomes a flood. So as modelers, we have to make a lot of assumptions about those formations, and that can lend to error. We'd love to reduce that error as much as possible. When I talk about microphysics, I'm referencing all of the precipitation particles that make up a singular cloud that in turn make up the variety of clouds that are occupying what we call a storm system. So whether a thunderstorm, a hurricane, et cetera. Those are usually called hydrometeors, and they are the liquid, solid, as well as mixed phases. Looking at the legend or the image on the right-hand side here, this gives us a visual. We're talking about the smallest cloud droplets that form from vapor. Those grow into rain droplets. At the melting layer, we start to formulate the graupel or small hail, and then of course above the melting layer, we are thinking about snow and ice crystal formation. The science questions that I've been evaluating so far are first, is there a microphysical sensitivity to sub-kilometer grid spacing for a landfalling hurricane? This really has not been researched in the past, so it became something that I was really interested in as I started my research. If that sensitivity does exist, then what is the impact to modeled flooding? And then finally, in the last year, as I've moved forward, I've asked, does this exist inside the hurricane only, or do we see similar behaviors across a spectrum of severe weather events? And this is, again, something that has not been addressed in the past. So whenever we are looking at global, regional models, thinking about climate or storm systems, we first have to cover our area of interest with a grid spacing, of course, with a grid, of course, that's going to allow our variables to evolve in time and space. For my weather modeling, I use Cartesian grids, so we'll be thinking about grid spacing in squares. Typically for a hurricane, we're on the order of 1 kilometer. 1 to 4 kilometers has been shown to really improve our knowledge around convective behavior in hurricanes. However, we are often not able to reduce that to get closer in the order of 100 meters simply because the computational demands have been too great. So that's been a really wonderful part of my fellowship, is being able to get down to 0.2 kilometer resolution and get finer resolved features inside my hurricane storms as well, but hurricanes, this is really a brand new ability. And generally, folks that have been able to get reduced grid spacing have had to use smaller domain sizes, so being able to use a larger domain with my fellowship's resources has really been incredible. However, I of course still need to note that precipitation particles are orders of magnitude smaller than that 0.2 kilometer grid spacing, so we are still using parameterizations and making assumptions about how those particles form. In my early research, I focused on Hurricane Florence. Florence made landfall in 2018 in September in North Carolina, bringing record-breaking flooding, and also was unique in the sense that Florence remained on land in the same area for about 3 days post-landfall. So that allowed me to think about the temporal evolution of flooding, not just a singular fast event. The model that I use is the Weather Research and Forecasting Model, or WRF, and my model setup is here on the left-hand side. I'm using a fixed outer domain. I don't know if my laser is pointing correctly, but the outer fixed domain is at 5.4 kilometer simulation, and then I have 3 moving nests. Those nests follow the eye of the hurricane as it evolves in time and space, and those nests vary in resolution from 1.8 down to 0.2 kilometers resolution. So I have 9 simulations total. I'm varying by adding 1, 2, or 3 nests to increase resolution across my simulations. And then I'm also using 3 different microphysics parameterizations to note the differences that occur according to this resolution dependence. When the microphysics schemes that I'm using are all similar in the sense that they are double moment. Double moment means that they predict both the particle's mass as well as the number density for each class of particles. However, they are different in that they are double moment across some classes and not all for each of the different schemes. So the WRF double moment 6 class, or WDM6, is only double moment in cloud droplets and rain, so liquid hydrometeors. The Morrison is double moment in all except for the cloud droplets. And then the predicted particle properties, or P3 scheme, is double moment in rain and total ice. The P3 scheme is novel. It is a brand new approach to microphysics, and it allows ice particles to evolve in time and space freely, which is brand new. So we're getting a more natural habit structure in crystal formation, where older schemes only classified snow or ice particles directly, so made assumptions that were less accurate. When we think about hurricanes, we always think about track and intensity. So I'm using this just to speak to what literature has often relied upon. What we always want to know is, where is that hurricane going to land and how strong is it going to be? And early literature has shown that if we change resolution, we increase the resolution, we don't really see a lot of improvement in the track or the intensity. So track on the left-hand side, intensity on the right-hand side there. It's not surprising to find that these simulations all look fairly similar to each other. The results that I show going forward, the 0.6 kilometer simulations will be solid or thicker lines here, and the 0.2 kilometer simulations are dashed lines, or the thinner lines here. And my microphysics schemes are gold for WDM6, blue for Morrison, and green for P3. When we think about the visual nature of how these microphysics schemes differ, we're looking at 0.2 kilometer simulations as the hurricanes evolve in space and time here. The WDM6 scheme in the upper left-hand corner has more texture, more granular nature to it that looks a little bit more like the observations that we see in the bottom right-hand corner, and that evolves just a little bit more close to the observations. The Morrison scheme in the upper right-hand corner tends to produce a lot of snow. Again, those assumptions for snow are less accurate than we would like, and so we lose the banded structure that we expect to see in a hurricane. The P3 scheme does begin with the Morrison assumptions, but then the ice microphysics are developing more naturally, so we start to see a little bit more banded nature, but still more rain than we are seeing in the WDM6 scheme. When we think about the spatial distribution and how that changes with varied resolution, I was actually surprised to see that there's very little dependence here on resolution. We see more, if I look from left to right, 0.6 to 0.2 kilometer simulation, they don't really look a lot different. There's a little bit more difference when we change the microphysics scheme. This is 3 days after landfall of accumulated rainfall, so the entire amount of flooding that occurred from the simulated storms. And so that time may allow us to accumulate in the same area more, and it just doesn't depend as much on the resolution. We do see an increase in rainfall, so the maximum rainfall total does increase as we increase the resolution. However, when we start to look at the hydrometeor classes themselves, and these are looking at vertical profiles, then I started to see more differences. WDM6 especially could have a factor of 2 to 3 times difference when I use the 0.6 versus the 0.2 kilometer simulations. And notably, I started to find that there was a difference in time. So for the Morrison and P3 schemes, if I'm looking at 12 hours within the landfall period versus 24 hours after landfall, then we would switch where 0.2 kilometer simulations would produce more mixing ratio of hydrometeors than the 0.6, and it was 0.6 in earlier times. So time really mattered in this sense of resolution dependence for the Morrison and P3 schemes. looking a little bit more holistically at the resolution. So as I go across the x-axis, I've got 1.8 kilometer down to the 0.2 kilometer. And I'm just looking at three different hydrometeors here, or excuse me, three different variables here, the liquid hydrometeors, frozen hydrometeors, and surface rain rate. But regardless of what I started to look at, the consistency was that there's this nonlinearity happening around the 0.6 kilometer simulation. So it really started to suggest that there was a gray area in that 0.6 kilometers, so not quite resolved enough that we're getting turbulence and not and in higher resolution than that 1 to 4 kilometers. So we're starting to get more precipitation developed. So as the last year, I've started to move that into if this happens in a hurricane, does it also happen in other storms? So looking at continental convection, do we start to see some of the same resolution dependencies, or is that different? I did my practicum at PNNL because they had led this cloud aerosol and complex terrain interactions field campaign from October 2018 to April 2019 in Cordoba, Argentina. Cordoba province is located in the north central part of Argentina here, and when we zoom in, we see the Sierras de Cordoba mountain range. This marker just indicates where the cacti field campaign radar was located. There's a 1 degree observational radius around that, and that mountainous area produces some of the greatest convection worldwide. So the largest hail, the extreme flash floods, long lasting rainfalls that can produce flooding over a period of time. So it offered a lot of great data for me to take different storms and analyze those. I am looking at 2 observed storms from the cacti field campaign, simulating those very similarly to what I did with the hurricane. The difference here is that I do not have an outer fixed domain at 5.4 kilometer simulations on land. We have other weather patterns that are happening in the greater region, and I don't want to absorb those into my simulation, so I'm using only the 1.8, 0.6, and 0.2 kilometer domains, but generally the nests are about the same size and behave the same, except that there's no need for them to move. They're not following a storm. I'm using the same microphysics schemes here with the WDM6 again producing lighter rain, the Morrison producing the larger swaths of rainfall. P3 is a little similar to Morrison with a little bit more texture. It also notably evolves slower in these continental storms than it did in the hurricane. When I'm looking at accumulated rainfall, so the full flooding that occurs from these simulations, there is a difference when we start to move towards 0.2 away from the 0.6 kilometer simulation. So spatial distribution of rainfall does seem to have some resolution dependence here. And this could just be, again, a shorter acting. This is 6 hours versus 3 days. So that might be the greater reason for the difference in resolution dependence here. However, when I look at the vertical profiles of hydrometeor classes, there isn't nearly as much difference between the resolution or even as much between the microphysics schemes, except for the P3 starts to loft these ice crystals into the higher upper atmosphere where it did not as much in the hurricane. Otherwise, there's less sensitivity that I'm finding in these continental storms versus in the hurricane. Again, looking at a same analysis, we do tease out this 0.6 kilometer nonlinearity that's happening with resolution as we move closer into the higher resolution, but not quite down to 0.2 kilometers, which can start to resolve turbulence in our storms. So just thinking about this holistically so far, I have found that yes, we do have microphysical sensitivity in the sub-kilometer horizontal grid spacing in a landfalling hurricane, and that does increase the modeled flooding. It also varies the precipitation rates and really changes in time. That resolution dependence does appear to be greater in hurricane simulations than continental storms, and this 0.6 kilometer resolution really seems to be a gray area where we're not quite resolving turbulence, but we are getting more precipitation, and so it may not be quite as accurate as we would like. And in my final chapter, I'll be looking at the why behind these findings. So in order to do that, I'm going to focus on the specific pathways that precipitation takes in order to become that surface rainfall. And again, I'd just like to say thank you to the CSGF and to the Krell Institute. It's just been so supportive over the last 4 years. And thanks to my collaborators at the University of Miami, Brookhaven National Laboratory, and Pacific Northwest National Laboratory. I'll take questions.